So in this lecture series we shall learn how we can analyze and how we can design a pre-engineered building structure for American standards. And in this lecture, as in the initial lecture series, we have learned a lot that how we can analyze and design a three-dimensional pre-engineered building structure. But in this lecture I shall teach you how you can design that along a particular span only, or in a 2D plane analysis. So first of all, we shall start with introduction of how we can analyze and how we can calculate wind loading and seismic loading as per the American standards, that is ASCE 07. So there is a lot of literature available on the internet free of cost that can guide you about the various codal provisions that are there in the ASCE 07. The latest code provision was released in the year 2016, but you can refer to ASCE 0710 also, because that is an somewhat older code, but a lot of literature is available on the internet regarding that code. So there's a very good website here where this Professor Samir has written a very good detailed explanation regarding calculation of seismic codes and regarding calculation of wind loads as per the ASCE 07. So I want you to go to this site.iugaza.edu.ps SSHIHADA. So here you will find the page of this Professor Samir M. Shihada. Go to downloads and go to this ENGC 6336. So here I want you to download handout number 10 that was released in the year 2018. And handout 10 deals with basically a detailed explanation of how you can calculate and how you can analyze the wind loads. So if we open this handout number 10 2018, so the title is Calculation of Wind Loads on Structure according to ASCE 0710. I am repeating again here that the latest ASCE 07 was released in the year 2016. But in wind there were not much major changes, but the purpose of this lecture is to explain you about the various aspects and how you can calculate the wind loads. So the design wind load for buildings and other structures, including the main wind force resisting system, that is MWFRS, and component and cladding elements thereof, shall be determined using one of the procedure as specified in the following sections. Now this line is giving us the basic preview. How it is giving the basic preview, that is for component and cladding calculation is different, and for the MWFRS, that is main wind force resisting system, the calculation is different. And if we first of all start with MWFRS, so under the MWFRS there are again two types. One is a directional procedure, second is the envelope procedure, and third here it is explaining the directional procedure for building appendices, that is rooftop structures and rooftop equipments, or it can deal with solid freestanding walls and solid freestanding signs, chimney, tanks, etc. So understand this page like this. First of all, there is this one table called this how to calculate wind load. Under the wind load there are two different types. One is this MWFRS, second is this wind tunnel procedure. And under the MWFRS there are again two types. One is the directional procedure, second is the envelope procedure. Directional procedure can be done for buildings usually in the range of 160 foot, but envelope procedure is usually when in the case of low-rise buildings only, that is maximum it can be used in for the height of 30 foot or approximately 9 meters. So right now we are talking about the MWFRS only, and for building appendices the provisions are different, and for the building having very large heights or very complex arrangement, the code guides us that we should go for the wind tunnel procedure. So there's this chart here, that is it. What it basically says that the if you can open ASCE 0710, if you have a copy of that, there are various chapters. So from chapter 26 to chapter number 31, it explains all the provisions for the wind loads. So chapter 26 deals with the basic factors that are governing the design of the wind. So here we can see that this is basically chapter 26 can be used to calculate or to find out the basic wind speed V. That is, there are various maps drawn for the US only, which shows what is the basic wind speed that we need to refer. Or you can refer to hazards.etccouncil.org website also to check what exactly is the basic wind speed V given. After that, second is the wind directionality factor KD. Third is the exposure category, topography factor KZT, gust effect factor, and closer classification and internal pressure coefficient GCPI. So if you are not familiar with American standards, all these terms might be an alien for you, and if you are reading an wind load standard for the first time, then I suggest you that this lecture might not be sufficient for you to get all the concepts. Wind loading and seismic loading, these two are a very wide domain subject that needs to be understood with the help of practical examples only. So yeah, in my recommendation, if the more you solve the practical examples for the wind load and seismic loads, the more you shall be comfortable with that. It doesn't matter whether you read 100 or 200 or 300 pages of this literature for the seismic and wind loading, but if you do not solve the practical examples, then you might not be comfortable with the calculations. So coming back, basically chapter 26 is the chapter which deals with giving you the raw data that you can cook to calculate or to find out the final design wind pressure. I shall give you the basic brief preview. That is, basic wind speed is the V, wind directionality factor KD, and topographic factor KZT. So directionality factor KD is something that usually varies with the height also. And if you are comfortable with the Indian standard, let us say this is like a K2 of the American standards. So in Indian wind loading also, there are 4 K factors, that is K1, K2, K3 and K4. So here basically KD denotes the wind directionality factor. Topography factor KZT, in Indian standard it is known as K3 factor. So in topography factor, it can be KZT is usually 1 when we are talking about the flat lands, but when we are talking about the building which is on the top of the mountain, then we do need to calculate the KZT factor. Now gust effect factor. Gust effect factor is something that that is like the basic crux or the basic engineering calculations concept that you do need to understand. So gust effect is like, what basically happens is that when the wind is being applied on a structure, and when we are saying that suppose we are talking about 1.5 kilonewton per meter square wind pressure, so it is not like it is continuously varying or it is continuously there for the whole time. It is like it puts a pressure for, let us say, American standard consider 3 seconds. So the peak pressure remains there for the 3 seconds and then it comes down, and then after some time it again gets on the peak pressure of, let us say, 1.5 kg per meter square, and then it goes down. So gust effect factor is a factor which depends upon the rigidity of the building. So American standard guides us that for rigid structure means that when we are talking about the concrete structures which are of low height, those structures are rigid. So for those rigid structures, we can consider G is equal to 0.85. Notice that this G is less than 1. Why? Because for rigid structures, the damping or the wind absorption in layman terms, so that damping is quite high for the wind. So what basically happens is that the absorption rate is high, so G value is less. But when we are talking about, let us say, slender structures can be like transmission towers or it can be like tall steel structures. So for those slender structures or for those flexible structures, we can say that the G value is dependent on the frequency and other various parameters also, and it can be more than 1 also. So G can be considered as 0.85 for simple low-rise structures or for simple low-rise rigid structures. But when we are talking about the flexible structure, it is recommended that we manually calculate the G, that is gust effect factor. So my wordings regarding this gust effect factor might not be clear to you, but we shall read a lot about this gust effect factor in the later part also. But this is a very important concept that you do need to understand. And I must say this is also a very common question that is being asked in the interviews also. So after that, enclosure classification. Enclosure classification is something that we can say a common sense. So what a common sense says that for a structure that is enclosed from all the sides, the internal pressure coefficients might be different. For a structure that is open from all sides, for that there shall not be any internal pressure. So external pressure, internal pressure is something. So external pressure is the basic concept that the pressure that is acting from the outwards, and internal pressure is something that is acted from the inwards. So we consider the accumulative or cumulative effect of external pressure coefficient and internal pressure coefficient to help us calculate the final basic wind pressure. So all these terms are something that you do need to understand very carefully. And after that, what it is saying that wind load on MWFRS and wind loads on CMC, that is component and cladding. So that already I had explained here, that for component and cladding the values are different. For the MWFRS, that is main wind force resisting system, the values are different. So now coming back to this chapters numbers. So basically from chapter number 27 to 31, it guides us about the wind load on the MWFRS. So for chapter 27 deals with the directional procedure, chapter 28 deals with the envelope procedure. So I am repeating again, directional procedure means that what basically it says that the wind loading is different on all the four sides. How? It gives us the different pressure coefficient on all the four sides. Whereas when we are talking about the envelope procedure, it only gives us one coefficient. So it is not dependent on from which pressure, from which side or from which direction the wind load is being applied on the structure. There is this one uniform coefficient that is given for this envelope procedure. And direction chapter number 29 deals with the building appendices, that is for example roof overhangs or parapets and other structures. And obviously wind number 31 deals with the what should I say, the concept that is not understood by most of the engineers, that is wind tunnel testing. So most of the people who are experienced in wind loadings are mostly from Australia or from New Zealand. So even I should say that, if I am not wrong, the Burj Khalifa that was designed, the wind loading was calculated by an Australian consultant. I don't remember their name, but whatsoever or whomsoever is designing the most typical structures on the planet Earth, they are getting their tunnel wind load testing from the Australia only. So after that we can refer to this chapter number 30 and 31. So chapter number 30 deals with the envelope procedure in parts 1 and 2, or directional procedure in parts 3, 4 and 5. So basically in these chapters only they had also explained regarding the wind loads on the components and claddings. So all those wind loads that we talk, let us say if you're talking about the British standard, I think was BS 8007 if I'm not wrong. If you talk about the European codes, the BS is superseded code. BS is not used nowadays because Britishers are also following European standards only with the British annexure. So if we talk about the European codes, the loadings are given in the EC1 if I'm not wrong. So For Indian standard, it is given in IS number 875, part number 3 for wind loading. In all those codes, for components and cladding, the wind loading is different. For the main wind force resisting system, the wind loading is different. So that is the basic concept. Overall, each and every country has written a different standards, but the basic concept or the basic derivability of the concepts, it is obviously the same. So as I discussed in some lecture also, that analysis up to analysis part, more or less all of the loadings or all of the reactions come at the same point. The difference happens in the designing part. So how we can determine the wind load? So first of all, it is given the risk category. So for any structure, when we start calculating the wind loading, we need to ascertain or we need to find out the risk category of that structure. So risk category of building can be taken from this table 1.51. So here we can see that, so for buildings that are represent a low risk to human life in event of failure, they can be classified in risk category number 1. For risk category number 2, that I shall explain. For risk category number 3 and 4. So for 3, it is saying that the failure of which would pose a substantial risk to human life. And buildings and other categories not included in this category 4 with potential to cause a substantial economic impact or mass disruption of day-to-day civilian life in the event of failure. So for risk category number 4, we can say that buildings and other structure designated as essential facilities, those which pose a substantial hazard to the community, buildings and other structures that contains or manufacture or handle or store hazardous fuels, hazardous chemicals or hazardous waste, or which contains some toxic substances also. So this is risk category number 4, risk category number 3, risk category number 2 and risk category number 1. Most of the times we are here in risk category number 2. So this is somewhat middle. So if we are talking about the simple structures, and we are not talking about the nuclear power plants, or we are not talking about, let us say, the metro stations, then we are dealing here with risk category number 2 only. So after that, the step 2 shall be to determine the basic wind speed V for the applicable risk category, that is A, B or C. So as I had discussed with you also, that is basic wind speed is a 3-second gust speed. So this basic wind speed is a different for different codes. It can go from 3 seconds to 1 minute to 10 minutes to 1 hour. So this is another important concept, that basic wind speed is different, is derived different for different design standards. So if we are saying that this basic wind speed V, let us say we are talking about the 100 km per hour, or let us say we are talking about 30 to 35 meter per second, let us suppose. So that 35 meter per second can be different derivation here for, let us say, Indian or Japanese standards. It can be different for European standard, and it can be different for the American standards. So whenever someone says that they need to design a building for 100 km per hour basic wind speed as per the American standard, so it means that it is a 3-second gust speed at 10 meter above the ground in exposure category C. So exposure category is also another concept that we shall learn after some pages here. So first of all, we can derive this basic wind speed V. We have already determined the risk category. After that, we can derive the wind directionality factor KD also. So to derive KD, we can refer to this page here. So here we can see that wind directionality factor KD, it is most of the time 0.85 here. That is for building main wind force resisting system, for components and cladding, for arched roofs. For chimney and tanks, it is somewhat higher. Obviously, these structures are not as rigid as the simple RCC buildings. So here gust factor goes somewhat higher value. Here we can consider 0.85, and for truss towers we can again take 0.95 for other cross sections, but for triangular, square and rectangular we can take 0.85. So after that he has also determined the exposure category. So this is the exposure category that was being talked about here. That is the 3-second gust speed at 10 meter above the ground in exposure category C. So when we are talking about the surface roughness C, it means that open terrain with scattered obstructions having height generally less than 9.1 meter. This category includes flat open country and grasslands. So when we are talking about the dense urban areas, then we are talking about the surface roughness B. And when we are talking about, let us say, the coastal regions, so in that we are talking about surface roughness D. That is smooth mud flats, salt flats and unbroken ice. After that, how we can determine the topographic factor KZT? So as we were discussing also, that if a structure is standing here, or if a structure is standing here, so here we can see that topographic factor KZT is basically nothing but square of 1 plus K1 into K2 into K3. So for flat terrain, obviously KZT can be taken as 0, no doubt, because for those flat region, K1, K2, K3, all these values are 0. So K1 multiplier, K2 multiplier and K3 multiplier, it is something which depends upon the value of H by LH, X by LH and Z by LH. So if we see about X by LH and H by LH and Z by LH, we can see here that he had explained all the values here. So this is the H that we are talking about. So this is the the height of the valley, and here we can see that H by LH, that is this region here. When we are talking about the X by LH value, we are talking about from this point to this value to this value here. And when you're talking about Z by LH, we are talking about this this value by this value. So we can calculate all these ratios, and similarly we can put these values here, and then accordingly we can calculate the KZT. So here he had explained that H is nothing but height of the hill. So here we can see that this is the height of the hill. After that LH is nothing but distance upwind of crust to where the difference in ground elevation is half the height of the hill, or escapement in feet or meters. K1 is a factor that accounts for the shape of the topographic feature. K2 is a factor to account for reduction in speed up with distance upwind or downwind of crust. And K3 is a factor to account for reduction in speed up with height above the local terrain. So X is distance from the crust of the building to site. Z is the height above the ground surface at building site. Mu is the horizontal attenuation factor, and gamma is the height attenuation factor. So gust factor G, obviously for rigid building it can be taken as 0.85. Enclosure classification, it can be open, partially enclosed or enclosed structures. So I repeat again that for open structures we don't need to worry about the internal pressure coefficients, and all building having each wall at least 80% open. So this condition is expressed for each wall with equation. Obviously E0, that is total area, should be greater than or equal to 0.8 times AG. So A0 is the total area of openings in the wall, and AG is the gross area of that wall in which A0 is identified. So if your opening area is greater than 80%, then it means that your structure is open. If your opening area is in the range of 20%, then it is partially enclosed. And for enclosed, let us first of all study the partially enclosed. So building that complies with both of the following conditions, that is total area of openings in a wall that receive positive external pressure exceed the sum of areas of the opening in the balance of the building envelope by more than 10%. And the total area of openings in a wall that receives this much is whichever is smaller, and the percentage of openings in the balance of the building's envelope does not exceed 20%. And for enclosed building, it is a building that is not classified as open or partially enclosed. So all those buildings which are not being fitted in either in open or partially enclosed, then we put them in the enclosed building classification. And internal pressure coefficient, obviously for open building it is 0, as we had discussed earlier also. For partially enclosed it is plus minus 0.55, and for enclosed building it is plus minus 0.18. And this is the concept that is most widely asked to me in the questions, that plus signs means that it is acting towards the structure, and away it minus signs denote it is acting away from the structures. So two values shall be considered to determine the critical load requirement. One is the positive value of GCPI, and the second is the negative value of GCPI. After that, we do need to determine the velocity pressure exposure coefficient, that is Kz or Kh. So Kh is constant and calculated for mean height of the building, while Kz varies with the height measured from the base of the building. So this is the table that has been taken from the ASCE. So here we can see that this is the height above the ground level. So they had classified that in the feet as well as in the meters, because 50 feet means that approximately 15.2 meters. So for that, as per the exposure classification, that is, it can be either B, C and D. So for those exposure classifications, we can determine these exposure and these values here. So here we can finally, after that, we can calculate the QZ value. So you should notice that if you had read the American standards, so they do give two types of formulas for each and every arrangement. One formula they give for the US units, second formula they do give for the SI units. So this is the formula that is applicable only for the SI, that is 0.613 into Kz into Kzt into Kd into V square. So when we are talking about the US units, this value is not 0.613 but it is 0.00256. So if we want to calculate the value of QZ in the US units, we do need to consider the formula, that is QZ equal to 0.00256 into Kz into Kzt into Kd into V square. So after that, we can also determine the external pressure coefficients. So this is the table that has been given, that is figure 27.41, that is most widely used when we are talking about the PEB structures or when we are talking about the monoslope structures. So this is the gable hip roof, that is, this is the gable roof, this is the monoslope roof, and this is the mansard roof. And wall pressure coefficients are given, that is for L by B having particular values, Cp is given. So wind pressure can be determined for each building surface by this formula here. So these are the various cases that has been given here. So if we consider the plan view here we can see that for case number 1, which can be considered, please focus on this part here, because this is the most important part. So when we are talking about the wind that is being flowing from this direction here, so we can apply UDL on this face, we apply UDL on this face, and on these faces also. So PWX, PLX, PWY and PLY. This is the case 1. Case 2, what basically case is here, that he has considered the this torsional moment also. So here what he had done is that 0.75 PWX, 0.75 PLX and 0.75 PWY and 0.75 PLY. So here he had considered the eccentricity also, that is plus minus 0.15 into Bx. So same value has been considered here, but with the factor of 0.563, and for case 3 we can see all these values here. So case 1 is the full wind design wind pressure acting on the projected area perpendicular to each principal axis of the structure considered separately along each principal axis. So case 1, I am repeating the line that has been written here. Case 1, what it denotes, that full design wind pressure, okay, acting on the projected area perpendicular to each principal axis. So when we are applying wind load along this face, it means that face we are talking about this perpendicular to the wind load direction. So if wind load direction is this, then face we are talking about is perpendicular to the wind load direction. So perpendicular to each principal axis structure, consider separately along each principal axis. So here we can see that there are there can be four cases here: number 1, number 2, number 3, and number 4. So under the case 1, there can be different 4 loading patterns. Case number 2. So case number 2 that we are talking about here is 3/4 of the design wind pressure acting on the projected area. So 3/4 means that 3/4, that is 0.75. So that is why 0.75 loading is acting along each principal axis of the structure in conjunction, that is along with the torsional moment. So this is the torsional moment. Case number 3. Case number 3 is this area. So wind loading as defined in the case 1, that is this part here, but considered to act simultaneously at 75% of the specified value. And case number 4 that we are talking about, it is nothing but it is saying that wind loading as defined in this case here. So whatever loading that we are applying here, they had taken the 75% of that value. So if you're good with maths, I should say, so 0.75 square is nothing but 0.5625. So that is the value they had considered here. That is 0.75 square is nothing but 0.563 that we are talking about here. So wind load as defined in case number 2, but considered to act simultaneously at 75% of the loading values. So design wind pressure for windward and leeward faces shall be determined in accordance with the provision of 27.4.1 and 27.4.2. So here they had also given an example here. So although I had started this lecture to explain you about how you can calculate the wind loading for a pre-engineered building structure as per the American standards, but to explain that we should at least know the basics. So I cannot just teach you grammar if you don't know the alphabets. So that is the basic thing that I follow. So if you want to learn the design standards for wind loading, I repeat again, do solve some practical examples. So there shall be first practical example here that we are talking about, and second practical example shall be our lecture only, that is how you can calculate the wind loading for the gable roof structures as per the American standards. So first of all, let us understand how he had derived values for this particular structure here. So this is the east, west, north and south. So here it is saying that it is required to calculate the lateral wind load acting on the 8th story. So height of the building is 8th story building. Considering the wind is acting first in the north-south direction, that is this direction. The building is used as headquarters for police operation is 30 meter by 15 meter in plan. This dimension is 30 meter and this dimension is 15 meter. And it is enclosed. It is located right on the Gaza beach, that is flat terrain. So basic wind speed we can consider 100 km/h. And this is the height of the building, that's 25 meter. So 30 meter by 15 meter by 25 meter. So building risk category can be taken as 4. So if we open our classification of building risk category, so as this is a police building structure, so it should be like under the action of extreme winds and under the action of disaster, they should be safe. So that is why we can consider it to be building number 4. So buildings or structure required to maintain the functionality of other risk category 4 structures. So obviously police station is something that needs to be there under the action of extreme events. So that is why we had considered risk category as 4. Basic wind speed, that is the wind speed for 3 second gust at 10 meter height for exposure category C. It can be taken as 100 km/h. After that, building wind load parameters. So KD can be taken as 0.85. So if you remember this KD equal to 0.85, so this is the table that has been referred. So in our case, it is nothing but building main wind force resisting system. So we can take directionality factor KD as 0.85. After that, if we want the exposure category also, so exposure category is D. So as he had written here that it is located right on the Gaza beach, that is flat terrain, so it is the maximum loading criteria. So if you go to this page here, so when we're talking about the flat on obstructed areas and water surfaces, that is beach, then it is surface roughness D. So that is why he had taken exposure category D. KZT, obviously if it is located in flat terrain, then K1, K2, K3, all these values are 0. So that is why KZT can be taken as 1. Gust factor G is 0.85 for rigid building, that I had already explained many times. After that, building is enclosed as per this provision here, and internal pressure coefficient for enclosed building is nothing but plus minus 0.18. So after that, we do need to calculate the KZ and KH. So KZ and KH for this here referred from interpolating from table 27.3 and 1. So here this is the table that he is talking about. So if we see the table here, it is saying that 24.4, 27.4 and 25. So he had finally taken 25 and 1.384. Why he had taken 25 loading value? Because the height of the building is 25 meters. But why interpolation is required, that we shall see in the table. So here we can see that he had not given any particular value for this 25 meter value. So here we can see that it should be in like here between 24.4 and 27.4 and between 1.38 and 1.40. So here between 1.38 and 1.40 for 25 meter, the value comes out to be 1.384 by interpolation. So after that, we do need to determine the velocity, pressure, QH and QZ. So if we talk about this value here, so QH is nothing but 0.613 into KH into KZT into KD into V square. So both of these formulas might be looking familiar or similar to you, but here we can see that this is the KH. So to determine the QH, we calculate KH, and to determine the QZ, we calculate the KZ. So obviously KH is 1.384 that we are talking about. So and KZ is something that varies with the height, and here we can see that 0.613 into KZ into KH into KZT into KD into V square. KZ we had already understood how we had calculated by interpolation from table 27.31, and KZT obviously is 1, and KD is 0.85, and V is nothing but this 100 meter per second divide. What he had done is that 100 kilometer per hour. So he had calculated that value in meter per second. So 100 kilometer is 1 lakh meters and 1 hour is 3600 seconds. So that is why he had divided it by like this. So when we are talking about the QZ, he had referred the value for KZ, and all these remaining values are same here. So he had calculated QZ as approximately 402.05. After that, if you wanted to calculate the external pressure coefficient CP, so for calculation of CP, we do need to find out the L by B value. So here we can see that L by B is nothing but 15 meter by 30 meter, that is 0.5. So if we want to calculate the this external pressure coefficient CP, we do need to be familiar with 27.4.1. So this is the figure that is being talked about. So here we can see that our L by B value is approximately 0.5. So for 0.5 L by B value, for windward face it is CP 0.8, and for leeward face it is approximately minus 0.5. So let us check what exactly is he saying. So if we talk about this QHGCP minus QIGCPI, G is obviously 0.85 for both the values. CP and CPI is something that we should know. So CPI is plus minus 0.18 as it is an enclosed structure. So CP is 0.8. So if we see the values here we can see that CP is 0.8 irrespective of the L by B values. That is what he had taken in this calculation here. So he had calculated the pressure in the terms of QZ. So for windward walls it is like this, but for leeward walls it is depending on the L by B ratios. So if for leeward walls it is something in this particular area. So here we can see that CP he had taken as minus 0.5. CPI obviously these values are same. So he has determined for leeward walls for this particular values. Some of you must be thinking what exactly is the windward, what exactly is the leeward also. So when we are talking about wind acting from this direction, so this is the windward face, this is the leeward face, and this is the sidewall face. And when we are talking about, let us say, this particular wind direction that is being shown in this figure, this is the windward face, this is the leeward face, and these two are the sidewalls. So for the sidewalls, if you want to calculate the value of CP, we can refer to this particular table here. So for sidewall, for all values, CP value is minus 0.7. So that he had taken here. So for sidewalls, he has calculated the pressure of minus 416.21. Now you must be thinking why he had taken this pressure as the function of this value, that is QZ. QZ, as we had discussed earlier also, that it depends upon the height. So if we are talking about height, then this value is different. So why it is different? Because it is depending upon the KZ value. So here we can see that he has not input any KZ value here. And if we see our basics, so this is the table that determines the KZ. So for different height, KZ value is different. And if we see our table here, so KZ he has calculated for 0 to 0.46 meters. It is KZ is 1.03. So here we can see that for 0 to 0.46 it is 1.03. For 6.1 meters, for 4.6 to 6.1 meter it is 1.08. So if we are talking about, let us say, up to this value here, so it should be 1.03, 08, 12, 16, 1.22. So we can go to the bottom table here. So here we can see that he has copied all the values here, and accordingly he has calculated the QZ. And after putting the QZ value here, he had calculated the pressures. So these are the different pressure which is varying as per the height. So obviously in the layman language also, for the basic understanding, obviously when we go up, the wind pressure becomes higher, and when we go down, the wind pressure becomes lower. So the more we are going down, the wind pressure is decreasing, but when more we are going up, the wind pressure is increasing. So this was the basic example that had made things clear to you. So when we are talking about wind flowing from this direction, windward phase it is 0.8, for leeward phase it is minus 0.5, and for both the side walls it is minus 0.7. So I hope the wind load concept is now clear to you. So in the next lecture we shall consider a real life example, although this was also a very good real life example that the Professor Sharif has explained in his handout. And I must say this is a very simplified explanation of a very technical code, because if you refer to the code first time without referring to any this explanation here, you might end up getting confused. So he has explained all these things in a very simple and elaborate manner, and I must wholeheartedly thanks Mr. Professor Sharif to give us this very good detailed handouts that can be very fruitful for learning engineers. So I hope now you are comfortable with the wind loading design standards, and I shall request you to write all these values here, write all the formulas and try to remember them, so that you may uh, understand these concepts easily. What exactly are the different types of enclosure in our buildings, what are the various internal pressure coefficients, how kzt and how kh and kz varies as per the height, how you can determine for gable, monoslope and mansard roofing arrangements. He has already although given only wall pressure coefficients for this simple buildings, but there are many other tables also that has been given in the American design standards. So in the next lecture we shall start with how we can calculate the PEB loading for 250 foot by 200 foot and for the 53.3 foot height of the portal structure. And as discussed, we shall not draw 3D full 3D structure. We shall draw a simple portal. We shall model a simple portal and then try to analyze and design it in STAAD software. So in this lecture we shall model a planar portal frame and analyze and design it as per the American standards. In addition, we shall work in FPS system, that is foot pound and second systems, or they are also termed as English units. So first of all, I want you to change it from space to plane, as we are doing a planar analysis. So this will also be a reference for you that how you can do the analysis of a typical portal structure in a plane. So you do need to select the STAAD plane instead of STAAD space. After that, after input width at 79, you need to enter units as feet and pound, and joint coordinate you can enter it as 1, 0, 0 and 0. So now if we are talking about let us say some force area, force over an area, then we shall talk in PSF, that is pound per square foot. And when we are talking about some distance, then we are not talking about in meters, we are talking about in feet. So write this command here, that is unit as feet and pound, and joint coordinates as 1, 0, 0 and 0. So after that we can press again shift plus K option, and in this calculation, so here we can see that the structure right now under consideration is 250 feet by 200 feet. So this is one span of the portal that we are talking about here, and in addition to that it shall be comfortable if we take a column in between also, because we cannot design a single portal of this 200 feet span, because it 60 span feet span, this 200 feet span is huge. So we shall break that span with the help of a column in the middle. And we do need to understand here that there shall be many portals here. So the spacing of portal, that is in our hands, and as I told in some other lecture also, that the most economical span is in the range of this 25 foot only. So we can divide this whole arrangement into 10 different arrangement of 25 feet each. So the base spacing for this example shall be 25 feet. So that you do need to remember. So after that, what we can draw in STAAD is that this height that we are talking about is approximately 20 feet. So this is the eave and this is the apex. So the height of the apex is 53.3 feet and the height of the eave is only 20 feet. So I was talking to one engineer, and what he said that this is an Adam and this is an Eve. So we don't need to make these type of wrong things. So this is called an apex, APEX, and this is called the Eve, so EAVE. So the height of the apex is 53.3 feet. So if we want to draw a portal here, so we can press Ctrl C, Ctrl V. We can select X as 100 and then again X as 100. So this height is 20 feet. So we can select Y as 20 and this height is 53.3 feet. So we can draw a portal here. So this is the portal on which we shall do our working. So this is 200 feet, and this is 100 feet, this is 20 feet, and this is 53.3 feet. So things are now clear here. So after that, if we want to calculate the dead loads and live loads first, so what we can do here is that we can go to general load and definition option, and under this option we can select this dead load and live load, wind load, WLX. So we can name it as WL1, WL2, WL3 and WL4. So here we can select dead load. We can go to the self weight option. We can take 5% for the 5% for connections. Now the weight of the sheeting and everything on the top, it is not more than 25 to 30 kg per meter square. That is 0.3 kilonewton per meter square. So we can go to this convertunits.com option. So we can go to the website, and here we can find out that it means 6.27 psf, or we can take 6.3 psf for the as a floor area. And now we need to multiply it with bay spacing. So 6.3 needs to be multiplied with the base spacing, that is 25 feet. So it comes out to be 157.5 pound per linear foot. That is, it is also called PLF. So we can go to this option here, left click on add, go to member load, uniform force, and this is pound per feet. So we can enter here as 157.5. So we can left click on add here, and we can assign this force to these two members here. So now the loading is correct here. After that, similarly, as per the American standards, we can take the live loading as 0.57 kilonewton per meter square. So we can have this loading as, we can calculate it here, that is 0.57 comes out to be 11.91, or we can take it at 12 psf. So 12 psf, we need to multiply it with 25 feet, that is base spacing. So it comes out to be 300 PLF, that is pound per linear feet. So here we can select it as minus 300. So we can assign this force to both of these members here. So now dead load and live loads are assigned. After that, the main thing, or the main focus of this lecture, that how you can calculate the wind load. So to calculate the wind load, I had attached this PDF for your easy reference. So here we can see that the angle, that is this pitch is approximately 18.4 degree, and mean height is 36.6. Mean height is nothing but 53.3 plus 20 divided by 2. So it comes out to be 36.6 feet. So this mean height is also a parameter if we want to calculate the wind load as per the American standards. So general wind load, we can take it to be 115 mph. Risk category, we can take it as 2. Velocity pressure coefficient KD, obviously we can take it as 0.85. So that we had already discussed in the previous lecture. Ground elevation above sea level, we can take it as plane. So here in that case we can see that our ground elevator factor KE comes out to be 1. Exposure category we can take it as C. We can take it as enclosed building. So for enclosed, obviously I had explained that you can consider the internal pressure coefficient GCPIS plus minus 0.18. Gust effect factor GF can be taken as 0.85, and minimum design wind loading that needs to be applied in the structure comes out to be 8 PSF, that is pound per square feet. So topography factor is not governing here, so we can take KZT also as 1. And as discussed in the previous lecture, that is this formula is different for US units and different for the SI units. This value is 0.613 for SI and 0.00256 for the US units. So this formula you do need to remember, and moreover, if you will practice, obviously you can easily remember all these things here. So this is the thing that we had already discussed in our previous lecture also, that is this QZ value is function of KZ. So in our previous example we had taken it as function of KZ. So similarly, as we had calculated the KZ and QZ for different heights, that this is the same thing that is being done here. So for different Z values, KZ is coming out to be different, and accordingly QZ is also coming out to be different. So peak velocity pressure internal can be calculated as 29.35 PSF, and net pressure, that is Q into GF into CPE minus QI into G into CPI. So net force is nothing but this pressure into reference area. Now we shall not multiply it with area, as we are doing the portal analysis. We shall multiply it with the base spacing. So whatever P value that we are calculating here in these two cells, we shall multiply it with the base spacing. So I am repeating again this concept. This concept is somewhat confusing to the engineer who is doing all this for the first time, but those who are seasoned or experienced may find it very easy. That is, if we want to calculate UDL, I am explaining this in a layman or simple terms. If we want to calculate the UDL with the from the area loading, what you shall do? You shall multiply it with the dimension. That dimension needs to be perpendicular to the face on which we are applying that loading. So if we are talking about let us say this area here, so what exactly it is being done here, that suppose there are various 10 number of portals with this 25 feet spacing. So for each and every portal that we are talking about, there shall be 12.5 feet on the left effective area and 12.5 feet on the right. So the total effective area of that portal shall be 25 feet. So whatever loading that we are calculating, the unit is PSF, that is pound per square foot. So if we want to calculate a pound per linear foot, that is PLF. So to calculate PLF from PSF, we need to multiply PSF, that is pound per square foot value, with the base spacing. So I cannot explain more to this simple concept. So coming back to here, so as per this external pressure coefficient CPE, that is minus 0.36 and minus 0.57, please notice that these pressure coefficients are not given in this handout here. These pressure coefficients, that is minus 0.36 and minus 0.57, that can be referred from the ASCE 07 code. So as we are talking here that this external pressure coefficient CPE, that is minus 0.36 and minus 0.57, this table was not given in the handout. So for that we do need to refer ASCE 7 2016. We do need to refer figure this 27.31. So here we can see that the code has given wall pressure coefficient CP and roof pressure coefficients. Wall pressure coefficients are very easy, that we had also considered in the previous lecture. That is, if we want to calculate the wall loading, so this calculation has highlighted various areas, that is A1, A2, B, C and D, and A1, A2 are the loading for this, that is windward walls. So if you will see this diagram here, so this is the windward face, this is the leeward face. So A1, A2, basically he had divided into various heights, so this is classified as A1 and A2, and this is classified as B, and these two side walls are classified as C and D. So coming back to this basic calculation, so A1, A2 are the we need to refer coefficient for the windward, B we need to refer coefficient for the leeward, C and D for the side wall. And this is a simple formula, simple coefficient, 0.8 for the windward, and for leeward it is minus 0.3, for L by B up to 2, and for side wall it is minus 0.7. And here we can see that this 0.8, minus 0.5 and minus 0.7 is considered. So for this B face, that is, this is the leeward face. So for leeward face, if you refer the standard here, for leeward they had given three options. That is, when L by B is between 0 to 1, the CP value is minus 0.5. When the L by B value is 2, then the CP is minus 0.3, and then when L by B is greater than 4, the CP is minus 0.2. So in this example, if we consider the L by B ratio, so our L by B is nothing but 200 by 250. So if we divide 200 by 250, it comes out to be 0.8. So our L by B is in the range of 0.8, so we can refer to CP as minus 0.5. So in this example, we can refer CP as plus 0.8. Obviously for all values it is 0.8. Our L by B is in the range of 0.8, so we can refer CP as minus 0.5 for the leeward face, that is the B wind face, and for C and D, that is side wall face, irrespective of L by B all values, it can be taken as minus 0.7. Right now we are talking only about the wall pressure coefficients and wall pressure values. So we can calculate the CPE, and similarly we can calculate the peak velocity pressure QP. Now peak velocity pressure QP is can be calculated here. It is given in this PSF, and net pressure P can also be calculated here. So these are the values that we do need to multiply it with base spacing to calculate the UDL that we do need to apply on our model. Now if we refer to our previous formulas that we have finalized here, so for the walls, these coefficients can be taken, and peak velocity pressure and pressure can be easily calculated. Similarly for the roof, so for roof they had given this table here, that is for windward and for leeward. It is depending upon the angles. So our angle is 18.4 degrees, so it should come around here. And when H by L, so H is nothing but our mean height. So H by L, if we want to calculate, so for that what we need to do is that our H is 36.6 divided by L, that is 200 feet. So it comes out to be 0.183. So our H by L is less than or equal to minus less than or equal to 0.25, and our roof angle is 18.4. It is something around here. So our value should come between 0.3 and 0.5 by interpolation. So this value comes out to be minus 0.36. Similarly for the leeward face, that is this arrangement here, it should come between minus 0.5 and minus 0.6 by interpolation. So this comes out to be minus 0.57. So similarly we do need to multiply peak velocity pressure, and thereby we can calculate the net pressure. So We don't need to multiply here, but basically we do need to enter all these relations in the formula here, so that we can calculate the net pressure P here. So here we can find out that both of these pressures are acting away from the structures, and these PSA values, when we multiply it with base spacing, we can calculate the loading in PLF, that is UDL, that we can apply on the beams. So first of all, we shall apply this WN1 loading here. So first value that we do need to apply is this minus 14.34. So 14.34 into 25, so it comes out to be 358.5. so minus 358.5. We do need to make it away from the structure, and this loading always acts perpendicular to the direction of the member, so that is why we had considered local Y instead of global Y. So this loading comes out to be 358, and we do also need to multiply 19.47 into 25, so it comes out to be 486.75. So we apply member load and 486.75, and direction we can apply it as this local Y. So both of these loadings can be applied here. So now we are done with applying the wind load on the this roofing arrangement, but the loading on this part is still pending, that is the side walls. So for up to roof height 15, we can apply it as 11.35 PSF. From 15 to 20, we can apply it to 12.33, and after that we can apply this on the leeward side, we can apply minus 17.76. Now this is positive, that is it is acting towards the structure. All these values are negative, that is they are acting away from the structure. So in our model we have not modeled the side walls, so we don't need to we cannot apply these loadings, but we can model the separate portal for the side walls, and on those portals we can apply these loadings. So coming back to this example here, we do need to apply 11.35 up to 15 and 12.33 up to 20. So what we can do here is that we can left click on insert node, and we can enter distance as 15 feet, and after that we can apply a triangular loading or a simple UDL loading. So what we need to do is that we do need to multiply this 11.35 into 25, that is 283.75. Direction we can take it as global X, and it is now increasing from 283.75 to this 12.33 into 25, so 308.25. So we can apply 283.75 to 308.25. Direction we can take it as local X. So let us check that whether this loading is correct or not. So this is the direction issue. So now we can see that up to this level here, the loading is 283.75, and after that it is increasing to 308.25 on the top. So now we had considered the windward phase. After that we do need to consider the leeward phase, that is 17.76 into 25, so 444. So we can apply member load and 444. Direction we can take it as global X. So now these loadings has been applied, that is A1, A2 and B. These three loadings have been applied. We cannot apply C and D when we are talking about the 2D plane analysis. So now I hope after applying WL1 and after considering all these coefficients, I hope the values are now clear to you, that how you can, I hope you have now got the at least a basic idea how you can calculate the area loading and how you can convert it into the UDL loading, that is uniformly distributed loading, for this US standards or US design units. Roof load case 2 is nothing but when we are applying wind at 0 degree, that is, this is the wind we are talking. So this is the wind at 0 degree, and when we are considering about minus CPI. So first example or the first load case was this wind 0 and plus 0.18 GCPI, and the second case is minus 0.18 GCPI. So in that case we can similarly calculate the walls and roof load case. So for roof we can take the external pressure coefficient CPE as 0.14 and minus 0.57. So now you must be thinking that in this example we had considered minus 0.33 and minus 0.57. How in this example it is plus 0.14 and minus 0.57. So for that you need to refer this table here. So these are the values for plus CPI and these are the values for minus CPI. So when we were talking about the plus CPI, we had our angle was this 18.4 degree. So our value was coming out to approximately minus 0.36. That is this value here. But when we are talking about this table here, the value should lie between 0 and 0.2. So for 18.43 degree, our value comes out to be 0.14. Whereas for leeward, it is again same, that is minus 0.57. So that is why it is plus 0.14 and minus 0.57. Similarly, if we are talking about the wall load casing option, so A1, A2 and B we are talking about. So for that we can go to this table here. So these values should be same. So it is again 0.8, 0.8, minus 0.5 and minus 0.7. So but our net pressure here we can see that obviously it is different, because here we are talking about this plus CPI and for load case 2 we are talking about minus CPI. So all the pressure coefficient is same, but this net pressure is different. So for this roof load case 2, so for roofing load case 2, here we can see that we had already calculated this plus 0.14 and minus 0.57, and for walls we can again refer to this 0.8 and minus 0.7 for side walls, plus 0.8 for wind wall, and for leeward face we can refer it as minus 0.5. So if we want to now apply UDL for this roofing arrangement here, so on the windward face it is net pressure is positive, but on the leeward face it is negative. So 8.71 should act towards the structure. So we do need to multiply 8.71 into 25. So we do need to apply 218. So we go to this add member load. Here we need to enter 218 and GY. So we need to enter it as minus, as it is acting towards the structure, and this is acting away from the structure. So we do need to multiply 8.9 into 25. So it comes out to be 223. So we can enter 223. Direction we can enter it as local, and here we can assign it like this. So for that also we should select local only. So this is like it is acting towards the structure because this value was positive, and this is acting away from the structure as this value was negative. Now for walls we can refer it as 21.9 to 22.9 and minus 7.19. So on the conservative side, what we can do is that we can apply 22.9 loading only. So what we can do here, we can just go to this 22.9 into 25, so it comes out to be 573. So for windward face, A1 and A2 are the windward face, so it comes out to be this 573. So member load direction shall be global X and 573. So we can apply this loading. This loading is on the conservative side only. So if we want to apply loading like exact loading, so it shall be like this, but I am taking this on the conservative side. And here we can see that on the leeward face it is minus 7.19. Now positive is acting towards the structure and negative is acting away from the structure. So 7.19 into 25, so it comes out to be 180. So this loading 180 PLF needs to be applied away from the structure. So here we can select it like this and apply it like this. So now all these loadings are correct. After that we do need to take care of WL3 and WL4 also. So for similarly for roof load case 3, we can see that the coefficients have been taken as minus 0.9, minus 0.5 and minus 0.3, and for walls it is taken as 0.8 and minus 0.45, minus 0.7. So now you must be thinking that suddenly these coefficients are now different. Why they are different? Because the direction of wind is different. That is, now we are talking about the 90 degree. So when we are talking about the wind at 90 degree, this was the diagram for wind at 0 degree, and this is a diagram for wind at 90 degree. So when we are talking about the wind at 90, this becomes A and this becomes D, and the side wall becomes B and C. So here we can see that this is the side wall. This is the side wall. So this side face becomes C and D, and this is the windward face, that is A, and B is the leeward face. So this is the basic arrangement. After that we shall again take care of the coefficients that we are talking about. So if we go to this table here, so here we can see that for wind direction, these are the roof coefficients CP, and wind direction normal to ridge, and wind direction this normal to ridge. Now so for roof load case 3, the direction is wind at 90 and GCPI is 0.18. Now if you refer here, so here they had given normal to ridge and parallel to ridge. So for parallel to ridge they had given the values for different H by L and horizontal distance from the windward edge. So from this they had calculated these values as minus 0.9 and minus 0.5 and minus 0.3 for proofing arrangement. So if we refer to the table here, that is this is the A side, that is the windward face, this is the leeward face, that is B, and these two are the side faces, that is C and D. Now our arrangement is on C and D for this as the wind force is perpendicular to that, so we do need to refer C and D loading arrangement only. So for wind load case arrangement 3, we do need to take here this C and D values, that is 17.76 and 12.77. so what we can do is that we can multiply 17.76 into 25, so it comes out to be 444, and it is acting away from the structure. And here we are talking about the roofing arrangement. So we can take this member load and minus 444 local Y, left click on add here, and we do need to take it plus 444. After that for this what we need to do is that we do need to multiply 12.77 into 25, so it comes out to be 320. And both of these loadings are acting away from the structure. After that, we do need to calculate the wall loading also. So for walls, here we can see that for C and D the values are coming same, that is 22.75. so what we can do is that we can multiply 22.75 into 25, that is 568.75, and all these loadings are acting away from the structure. So we can refer here member load and minus 568.75 and global X plus and this minus and plus global X. So this shall also be acting away from the structure and this shall also be acting away from the structure. So now WL3 is also done. Similarly, we can assign WL4 also. So for 4 for the walls, we can see that it is 12.18 for C and D. So 12.18 into 25, so it comes out to be 305. So it's member load minus 305 and plus 305. And after that, for this for load case number 4 and roofing loading, we can refer here as plus 0.79 PSF. So for plus 0.79 into 25, it comes out to be 19.75. So we can take 19.75 and it is acting towards the structure. So again, let us cross check. The signs are positive, so it is acting towards the structure, and both of these loadings are acting away from the structure. So it comes out to be this minus 305 and plus 305. So now the dead loads, live loads and will loadings are applied for this particular portal arrangement here. So after that, we can go to this auto load combinations, AISC, general and generate loads. So now we have generated loads as per the American standards. If required, we can go for this repeat load case option also. And here we can left click on support, create, append and left click on add here. And after that, we can go to the property and we can, this length is approximately 105 foot. So we can divide it into 3 parts here. Similar for this arrangement. And we can go to this property and define. We can go to this tapered eye. Here we can enter depth of section start node as 3 foot, 1.25 foot. Thickness of web we can take it as 0.00. Let us say if we are talking about the web of this 10 mm, so 10 divided by 25.4. to be 0.4 foot. So 1 foot is 0.4 into 12 into 25.4. And depth of section at end node we can take it as 1.75 foot. Width of top flange we can take it as 0.75. thickness, and width of top flange we can again take it as 0.75. Now thickness is somewhat confusing part here, because if we are considering that thickness of, let us say, top flange is 16 mm, so what we can do here is that we can let us say if we are talking about 0.03 foot into 12 into 25.4, so 0.03 means that it is approximately 10 mm, and if we are considering 0.5 into 12 into 25.4, it comes out to be 0.05 into 12 into 25.4, so it comes out to approximately 16 mm, so we can take it as 0.05. So let us cross check the other dimensions also. So the width of top flange is 0.75 into 12 into 25.4, it comes out to be approximately 228 mm. So we can assign to this member here, and let us check in 3D. So here we can see that now the sections and everything is realistic. So from 1.25 to 1.75, we can again increase it to 1.75 to 2. So 1.75 to 2 foot, and 0.03, 0.05, so now everything is correct, and after that similarly we can assign a uniform section here. So we can go to this define option, tapered eye, depth of section start node 1.25, 1.5 to 1.5, 0.04, 0.06, 0.8 foot, left click on add here. Now let us check the orientation. The orientation of this member here is like this. So this member is resting on the web of this member. So what we can do is that we can go to the commands, geometric constant, beta angle, and 90 degree. Go to commands, geometric constant, beta angle, and assign it to 0 only. So now the orientation is correct, and now we need to assign the properties to these members also. So we can go to define, tapered eye, depth of section start node we can take it as 3.5 foot to 2.75, thickness of web we can take it as 0.03, 0.05, 0. We can take it as 1 foot only. As the depth requirement is higher here, so after that we have reduced it to from 3.5 to 2.75. Now again we need to reduce it from 2.75 to, let us say, 1.5, thickness 0.03, 1 and 1.05. So now the depth has been reduced to 1.5 foot here. So after that we again need to increase it to this arrangement here. So we can either mirror this whole arrangement here. So we can go to the tools, check tools and redefine incidence, and switch incidence of selected beams. Similarly, we do need to apply the same arrangement here also. Tools, and redefine incidence and switch incidence of selected beams, and after that we can take it like this. So now let us check this whole arrangement in the 3D view. So now this arrangement is looking somewhat realistic and okay. And although the slope is too steep here, but let us check the arrangement here. So we can go to select by specification and all failed beams. So go to select by missing attributes and missing properties. So all the properties have been assigned. Specification we don't really need to provide here. Supports we had already provided. Loads and load combinations we had already provided. We can go to analysis and add. We can go to the design section here. Now under steel we can go to this ASCE 360 10. We can left click on define parameters. Here first of all we need to go to the method here and select ASD. Here we can select FYLD and FU. So FYLD we can select it like that only, and LY and LZ we can also assign them. We can see the value of LZ here to be approximately 106 foot. LY we can take it to approximately 5 foot. LY, why we are referring it as a 5 foot? Because we shall all tie all the members at the spacing of 5 foot interval. So unsupported bottom and top we can also select it to be as 5 foot, because we shall provide the flange, upper flange and bottom flange bracing also. So UNT again we can apply to all the main members here. Similarly for the UNT also. Similarly for the LY also. LZ of 106 can be applied to the main members here. So we can go to commands and check code and take off. So now we can analyze this structure. So when we open the output file here we can see that it is string is a simple warning that applied self weight is less than total weight of all the members. So when we go to the option here, self weight, here we can see that self weight is missing for all these members here. So we can assign to view and again analyze and design this portal frame arrangement here. So here we can see that it is dominating in load case number 11. The ratio is coming out to approximately 0.67. The bending moment is in the range of 4604 KIP inches, and here it is in the range of 9970 KIP inches, and it is failing by some margin, that is 1.05. These members are also failing here. So here we can see that we do need to take care of this whole arrangement here. That is, right now the members are not passing. So we can increase the thickness of the web, we can increase the height of the web, thickness of the flanges also. So instead of 1.25 to 1.75, we can take it as 1.75 to 2 foot and 0.05 to 0.08, and we can take it as 1. So let us analyze and design the structure again. So if you see the ratio here, now the ratio has decreased drastically. So now the members are highly safe here. So now we can see that all the members are now passing. We can go to select by specification all failed beams, and we can see here that there is no contribution of MY, only there is contribution of MZ. So these type of things can only happen when we are selecting the stat plane from the editor file, because all the forces are being analyzed in a single 2D frame, not in a 3D space. So that is a major difference when we are talking about working in stat space or stat frame. So there shall be only one component of bending moment. There is no provision of this MY arrangement here. So we can also check the bending moment diagrams here. So this is the general bending moment arrangement. So we can go to the labels, scales, apply immediately, and decrease this bending Z value. So this is the typical bending moment diagram that has been shown for this type of arrangement here. So here we can see that the slenderness ratio is also good, that is 171. So these are the simple things that you can take care when we are designing the PEB sheds. So in this example, my purpose was only to explain you that it is not necessary that you do need to model a 3D frame. You can also model a simple 2D frame, and then you can just analyze and design this whole arrangement. We can just repeat this arrangement onto the remaining 8 parts also. Obviously for the side walls we do need to model them separately, and in addition we do need to calculate the bracing requirements manually only. So for bracing requirement, what we need to do is that we do need to either consider the total area that flows along that plane of the bracing, or we do need to consider the seismic loading also. So I hope the things are now clear to you, that how you can calculate the wind loading for pre-engineered building structure as per the American standard, and how you can analyze and design it only in a 2D frame.